Think of the Milky Way, or search for pictures of it online, and you'll see images of a standard spiral galaxy viewed face-on, a sprawling pinwheel of starlight and dust containing hundreds of billions of stars. These images, however, are mostly make-believe. We know the Milky Way is a star-filled spiral galaxy in excess of 100,000 light-years wide, and we know our solar system drifts between two spiral arms at its outskirts, some 27,000 light-years from its center. But much beyond that, our knowledge fades. No space probe or telescope built by humans has ever escaped the Milky Way to turn back and take a portrait because we are embedded in our galaxy's disk. We can only see it as a bright band of stars across the sky. For astronomers trying to map it, the effort is a bit like learning the anatomy of a human body from the perspective of a single skin cell somewhere on a forearm. How many spiral arms does the Milky Way have, and how do those spiral arms branch and curl around the galaxy? How many stars does the Milky Way really contain? How much does it weigh? What does our cosmic home actually look like, viewed from another nearby galaxy? Ask an astronomer, and if he or she is being perfectly honest, you will learn that we do not fully know. Among the biggest obstacles to our knowledge is the disk of the galaxy itself, particularly its center, which is thick with starlight-absorbing dust and rife with energetic astrophysical outbursts that can ruin delicate observations. This means we know very little about the other side of the galaxy. Optically, it's like trying to look through a velvet cloth, black as black can be, says Thomas Dame, an astronomer at Harvard-Smithsonian Center for Astrophysics CFA. In terms of tracing and understanding the spiral structure, essentially half of the Milky Way is terra incognita. Now, however, new record-breaking measurements are allowing astronomers to pierce the veil of the galactic center as never before, and to construct the best-ever maps of our galaxy's structure. Instead of using visible light, Dame and others map the Milky Way by looking for radio emissions from molecular gas clouds and massive, young stars, both of which typically reside in spiral arms. The challenge lies in measuring, in the absence of convenient intergalactic road signs or distance markers, how far off these objects are. Without knowing these distances, astronomers cannot precisely situate any given radio source within the galaxy to accurately reconstruct the Milky Way's morphology. Since the 1950s, astronomers have solved this problem using kinematic distances, calculations that treat objects in the Milky Way a bit like pieces of flotsam spiraling into a whirlpool because things tend to move faster as they approach the center. Measuring how fast an object is moving toward or away from us yields an estimate of its distance from the galactic center, and thus from our solar system. Kinematic distances have helped Dame and others discover previously unknown spiral arms and spiral arm substructures on our solar system's side of the Milky Way. But the technique breaks down for peering directly across the galaxy, where objects do not move toward or away from us at all but rather purely perpendicularly to our line of sight. To map the Milky Way's hidden half requires a more direct method. In a study published October 12 in Science, Dame and an international team of colleagues have demonstrated just that. Using the National Science Foundation's Very Long Baseline Array VLBA, an interlinked system of 10 radio telescopes stretching across Hawaii, North America and the Caribbean. The astronomers have directly measured the distance to an object called G007.4700.05, a star-forming region located on the opposite side of the galaxy from our solar system. The measurement showed the region to be some 66,000 light-years away, nearly 40,000 light-years beyond the galactic center, and roughly double the distance of the previous record holding direct measurement of distance in the Milky Way. The team relied on a time-worn technique called parallax, which measures the apparent shift in an object's celestial position when seen from opposing sides of the Earth's orbit around the Sun. You can see parallax on smaller scales simply by holding a finger in front of your face and winking one eye then the other. Your finger will seem to jump from side to side. Calculating its distance from your face is as simple as measuring the angle of its apparent shift. The smaller the angle, the greater the distance. And the wider the distance between your two detectors, be they eyes or radio dishes, the more acute your measurement can be. The VLBA's parallax observations took place in 2014, when Earth was on one side of its orbit, and then 6 months later in 2015, when our planet was on the opposite side of the Sun. This maximized the sensitivity of the technique, allowing it to measure the minuscule shift in the apparent position of the distant star-forming region. According to lead author Alberto Sanna, a postdoctoral researcher at the Max Planck Institute for Radio Astronomy in Germany, the VLBA's measurement is equivalent to seeing a baseball on the surface of the Moon. The feat, Sana says, shows we can measure the whole extent of our galaxy, to accurately number and map the Milky Way's spiral arms and know their true shapes, so that we can learn what the Milky Way really looks like. It really is excellent work. I believe this is the smallest parallax ever obtained, and it is certainly a milestone in modern observational astronomy, says Marikai Honma, an astronomer at the National Astronomical Observatory of Japan. Honma led a separate team that independently measured the distance to G007.4700.05 in 2016, finding a similar value. Those measurements, however, were not accurate enough to obtain parallax, and relied instead on tracking the star-forming region's so-called proper motion across the plane of the sky. The similarity between the two teams' results, Honma says, suggests proper motion alone can be a useful tool for determining distances to objects on the other side of the galaxy. Already, the confirmed distance for this particular star-forming region is redrawing galactic maps. In 2011, Dame and colleagues used radio measurements to tentatively trace the path of one spiral arm, called Scutum Centaurus. Their fragmentary measurements suggested this arm might wrap around almost the entirety of the Milky Way, but they lost its trail, and crucial evidence for its galaxy-encircling breadth in the vicinity of the dark, roiling galactic center. This star-forming arm runs right through one of the features we identified in 2011, and adds evidence that the Scutum Centaurus arm is really a major structure in our galaxy, Dame says. In 2011 we wrote that we may never sort this out, because proving its distance through the galactic center would be so difficult, but we were being short-sighted, because here it is. 6 years later, the VLBA's painstaking, Earth-orbit-spanning measurement occurred as part of a larger project, the Bar and Spiral Structure Legacy Survey Bessel, led by Mark Reed, who like Dame is a radio astronomer at the CFA and a co-author on the science study. Now in its concluding stages, Bessel used 3,500 hours on the VLBA to obtain more than 200 distance measurements for star-forming regions scattered throughout the Milky Way. Many of these readings are now tracing out new details in the galaxy's filigree of spiral arms, which is a good start, but being in the northern hemisphere, the VLBA and Bessel cannot survey most of star-forming regions visible from the southern sky. And even if they could, parallax alone will not fill in the galactic map. Because parallax measurements so difficult to obtain for far-distant star-forming regions on the other side of the galaxy, astronomers widely agree they will chiefly serve as important calibration points to augment existing kinematic distance measurements. Further progress will come from a combination of parallax, proper motion and kinematic distance data via surveys using Southern Hemisphere-based radio telescopes as well as from space-based data from the European Space Agency's Gaia satellite. The latter is using visible light parallax measurements to pin down the precise positions for 1 billion of the Milky Way's stars. Taken together, the resulting map will help astronomers pin down many still unknown fundamental aspects of our galaxy, such as how fast and uniformly it rotates. This will let them finally determine just how massive the Milky Way really is, potentially yielding new insights into our galaxy's inventory of stars, dark matter and small satellites that lurk at its edges. All of this will help scientists understand how the Milky Way first came to be, and much that has happened to it since. How important is it, really, for us to be able to see clear across to the other side of our own galaxy, asks Tom Benaya, a radio astronomer at Boston University involved in some of the southern surveys. It is the most important thing in all of astrophysics. It took humankind thousands of years to map the Earth accurately. A map of the galaxy will constrain about a dozen or so models of the structure and evolution of the Milky Way. To me, perhaps the holy grail of astronomy is to provide a clear perspective of our relationship to the physical universe. The map of our galaxy is a part of that, and that map is still incomplete. Soon, that could change. Thanks to Bessel and its ilk, Reed notes, in only a few more years we should have a map that shows us what the Milky Way really looks like.